All right, so position, velocity, acceleration. So now, as we get done with chapter 3 here and finishing up, being able to do derivatives, because this is it. We're not going to add any really new derivative rules. These are the derivative rules we have for the different functions. We can take any different combinations of functions and do them. For elementary calculus, it's kind of an oxymoron, isn't it? Elementary calculus. But that's what we would consider this, I guess, beginning calculus. But that's what we've got. So now that's what we're going to get into in chapter 4. Then is we're going to get into now what are the uses of derivative. We've already done some of that in chapter 2. We talked about local max min, all those chart problems, all that kind of stuff. So we've done some of that. We've just now broadened our ability to do derivatives of more complicated functions, so we can now revisit those ideas, and we can go farther into some more applications. So this is just kind of going back and revisiting these ideas, and to be honest, just getting better at it. We're going to look into the technicalities of it a little more. We're going to dig a little deeper into it, right? As we go into it, and then just get really better at it and more solid of our understandings of all these connections. So if x represents a position of particle on the axis time t, so this is something you got to get really familiar with, this notation, because on the AP test, they use this example a lot. Now, we started, the very first time we talked about derivative was Bismarck, right? The car moving east and west. That's just an x-axis, right? Why do we talk about a particle on the x-axis? Well, we could talk about a car going east and west of Bismarck. It's the same thing, right? What we want is we want to be able to describe just straight line motion, and we want to be able to talk positive being to the right and position, and we want to talk negative being to the left. Well, that's what an x-axis gives you. An x-axis gives you that, where there's Bismarck, and then here's 1 mile, 2 miles, 3 miles, 1 foot, 2 feet, 3 feet, whatever, right? And to the right is positive, and to the left is negative. So it just gives us a nice mark. It'd be like the interstate being marked every, whatever, and east was positive, west was negative, and so forth. So particle on the x-axis is just a way of doing a problem. And since its position is an x-coordinate, if that's the x-axis, and if I'm over here at 4, my x is 4. So t is the input, because I'm there at a certain time, but x is my output. So we got to get used to that. So x is actually, in problems like this, x is going to be, x is going to be my output, right? And so that's why input and output is so important. We're used to x being the input, right, in problems, but not here. In problems like this, x is the output. T is the input. Okay, so this would be dx dt. So there would be an x prime. Remember when we were talking about implicit differentiation? We said you don't do x prime. Well, not in an xy problem, right? In an xy problem, you're doing it with respect to x. The derivative is with respect to x. So x prime would be dx over dx, which is 1. Okay, but in this problem, there would be an x prime, right? There would be x prime of t, and that'd be the velocity, right? That'd be the velocity. And x double prime would be the acceleration. So we want to make sure we understand that notation. Okay, initially means when time equals 0 at the origin means position, or x of t equals 0. This would be t equals 0. At rest means what? Yeah, x prime of t would equal 0. I think would be a good way to write that. You could have put velocity, but let's understand notation x prime is 0. We're not going to go through all this, but there are a few things I want to talk about. If the velocity is positive, the particle is moving right. If the velocity is negative, the particle is left. The average velocity, you divide the change in position by the change in time. So that would be x of b minus x of a all over b minus a. Ready to go? You'll have to try to block out the top. So that would be, and remember, that's like average rate of change, right? That's the average rate of change. That'd be the change in position divided by the time, okay? Instantaneous, of course, is your derivative, the acceleration. If the acceleration of the particle is positive, then what is increasing? What'd you put here? Velocity, right? Because acceleration would be like x double prime. If the acceleration is positive, then the velocity x prime is increasing. That's just from the chart, right? If the acceleration of the particle is negative, the velocity is decreasing. In order for the particle to change direction, the velocity must change signs, right? It must go from positive to negative. Now, let's talk about a couple of things. Well, we can get to the speed part of it here in a minute. Here's number 11. I want to work through number 11 because I would be surprised if anybody got this one. I don't know. There should be. What do you got on
26 meters.
You got 26. What do you got?
36.
26? 36. All right, now let's make some sense of what this is, because this is actually a problem we're going to see a fair amount. This is the one that I want to do on here. Then there's some others on here that were like it that you can do on your own. Okay, but one way to determine total distance traveled over a time interval is the sum of the absolute values of the differences in position between all resting points. Here's an example. If the position is given by this, find the total distance traveled between 0 and 6. Now, one thought would be to plug in a 0. Did anybody think of that? Did you plug in a 0?
Yeah.
Okay. So you plug in a 0 and you get 4. And then plug in a 6 and you get 22. Okay. Now you added them together and you subtracted them. Okay. Now let's talk about what this means. What does this mean right here? That's, well, okay, but let's don't call it the y coordinate, let's use input and output. Remember,
Time to 0, you're 4.
on the x-axis, if this is 0, let's pretend, I should just paint an x-axis right now. This is 0, so I'm at 1, 2, 3, 4 on the x-axis at the start. And then what's the second one say? 6 seconds later, whatever, I'm at 22.
Yeah.
So, wouldn't you subtract them? You wouldn't add them, I don't think, right? So wouldn't that be 18? But what's that not taking into account? What is that assuming? That I went from here straight to there. But what could I have done? Well, I can only go this way. I can only go east-west. Couldn't I have went this way at first?
Yeah, but if you're measuring velocity, you want to use displacement, so it won't matter if you do what.
But it's not displacement. That's the difference. Okay? It doesn't say anything about velocity here. It just said this is the position function. What's the total distance the particle traveled? That's all it's saying. So, by subtracting them, you found displacement, didn't you? That would be net distance traveled. Okay? So if the question was net distance traveled, then that is just the beginning and the ending and subtract them in absolute value, right? I mean, if I started at 22 and ended at 4, I mean, because this would be 4 minus 22, which, right? I mean, it's absolute value. So it'd just be the net distance traveled is displacement, and that would be 18.
So when it says the absolute value of all the resting points, you don't give 0 to 1 and 1 to 2.
Well, no. Well, where do you get 1 and 2?
Just
No, but that's how it said. It said the resting points. What are the resting points? When it stopped, right? Now, if I start here at 4 and I go to 22, when do I stop? Well, I start at 0 and I end at 6, but what about in between? What if I go this way?
stop.
Don't I have to stop to turn around? Remember the chart? That's local max min stuff, right? When is the ball at its peak? When the velocity is 0, right? What's the first thing? Remember what I said, and you get to these problems, what's the first thing? If you don't know what to do, what do? Do the derivative and set it equal to 0, right? Because in this problem, what would that do? That would tell us when the thing stopped. So if I was going to go in a straight line from here to here, would I ever stop? I might. I could stop and then keep going. Flat spot, right? This is like a number line thing. This is like a chart problem. See, we haven't really done this much, though. We did do it, actually. We did do a problem where we said, you got the particle moving. When is it moving to the left? When is it moving to the right? Oh, when its velocity is positive, when its velocity is negative, right? So we got to do a derivative, set it equals 0, do a number line. That tells us a story. So the key is between all its resting points. Well, we need to find its resting points. So we need to do x prime. So we get t squared minus 2t minus 3, and then we got to do equals 0. Oh, that factors real nicely. So that's t minus 3, t plus 1 equals 0. So t is either equal to 3 or negative 1. We can throw out the negative 1, right? Right? So it only stops one time, right? It only stops one time, which is at 3. So what do we need to do? So now what did it say? One way. Now we're gonna have another way later on. We don't know enough to be able to do it right now. But so one way to get total distance traveled is to find how far it traveled between its resting points, right? So what do I need to do with that information right there that I just found?
0 to 3, subtract
Okay, say that again.
0 to 3 and subtract them, then 3 to 6.
Okay, so in other words, I need to put 3 into the original, right? So I need to put 3, and I need to see where I was, right, when I stopped. So let's put 3 into the original. 27 times a third is 9 minus 9 minus 9 plus 4. Did I do that right? I was at negative 5, so what's that tell you that I did? I was over here at 4. I went to negative 5, which is a distance of 9. Then I went from negative 5 to 22, which is a distance of 27, wouldn't it? Yeah, it'd be 5 plus 22. So I went 9 that way, and then 27 this way. And that is, and they say the absolute values because it doesn't matter which way you subtract them, right? So it's like 4 minus negative 5, and then it's negative 5 minus 22, which would be negative 27, but that absolute value. So we're at 9 and 27, which is that what you said? Is that how you did it? Good job. And here I bet nobody would have got that right. Good job. Do you do the derivative and stuff and all that? Said equals 0. Now, we didn't do a number line there, but we could have, but who cares? We actually know enough. We know that's right. We know it went left and then right? If we did a number line, we put a 3 on there, pick a couple numbers to plug in. If we put a 2 in here, that's negative, positive. Put a 4 in here, that'd be positive, positive. And what's that tell us? The particle did what? Left, then right. Left, then right. And we know that's the only time to stop. Right there. Okay, Cesar, just wander in anytime. You ready? I know. I know. Just set it back a little bit. You can't use that.
Well, I know. I realize that.
Okay. Did you
I'll put that right
over
there.
real quick? Or
What?
You were looking.
Yeah, I was on the hallway.
On the way down. Okay, just set it back. All right. So that would be it, okay? So that's what it means by the absolute values of the differences in position between the resting points, okay? So there's another one of those scenarios in another page. So there's one last thing I'm talking. So then they get into some ones with tables, but I want to move on. We may take a little time tomorrow. Remind me, I want to take a little time tomorrow to do a few of these, but I think it might be this page right here. I think it's page right here. Find the total distance traveled. So this is page 9, number 4, right? Put a little note by that. That's just like number 11 on the back that we just did, okay? That's just like the one we just did. okay? And then, so let's talk about, let's go to this next page, which is page 13. Okay, this is where I want to just say a couple things. So speed is the absolute value of velocity. That is a mouthful right there. We have got to just understand that. So speed, whenever you hear speed, they're talking about this, okay? Now, and so we were talking displacement, we were talking about, right, velocity is, we really got to be careful. I guess what I want to say here is you've got to really be careful about using the word increasing and decreasing. Because speed increasing is not the same as velocity increasing. Your velocity can be increasing, but your speed be decreasing. You can be slowing down. Think about it. If my velocity is negative 20, and then my velocity goes to negative 10, what just happened?
Speed sped up. Or velocity sped up 10.
Yeah, be careful with the word sped, right? Because that means speed. So if my velocity goes from negative 20 to negative 10, I'm slowing down, but those numbers are increasing. Negative 20 to negative 10 is an increase. So the velocity increased, but the speed decreased. Now graphically, here's what's happened. If you take a velocity graph that goes like this, right? Well, the velocity is increasing whenever this graph is going up, right? Well, right here, the graph is going up, so the velocity is increasing. Right here, the velocity is going down. Now, so is the speed, right? Because the velocity is positive. When velocity is positive, velocity and speed are the same thing, right? When velocity is positive, velocity and speed are the same thing because the absolute value of positive is positive. So whenever this graph is above the x-axis, velocity increasing, speed's increasing. They're the same thing. But when the velocity is negative, then they're opposite. So down here, remember, when you do the absolute value, what do? You just take all of the negative parts and just flip them up to positive, right? So the red here would be speed, the blue would be velocity. So down here, the velocity is decreasing, but the speed is increasing because your velocity is going from negative 10 to negative 20 to negative 30, right? So you're getting faster, but the velocity is decreasing, right? The velocity is decreasing, but the speed is increasing. So you just really have to be careful on those two things. And then the relationship between acceleration, and we talked about this. Velocity and acceleration. If velocity is positive and acceleration is positive, or if velocity is negative and acceleration is negative, that's when something is speeding up. Okay, an option is speeding up or getting faster if these two agree. If the velocity and acceleration are both positive, and if the velocity and acceleration are both negative, then the object will be speeding up. Like in this case, the velocity is negative and the acceleration, which is its slope, right, are negative. So it's the velocity is down here and its negative slope, they're both negative, you've got an object that's speeding up, okay? But then again, it's slowing down, and so this is just something we just got to know. And so if the velocity is positive and the acceleration is negative, or if the velocity is negative and the acceleration is positive, then we've got an object slowing down. So anytime you get a question, it's speeding up or slowing down, you have to take both into account. You can't just say it's speeding up because the velocity is increasing. That's not enough. The velocity increasing is not enough because right here, the blue is the velocity. Right here, the velocity is increasing. But that object is slowing down because its speed is going towards zero, or its velocity is going towards zero. So just saying velocity is increasing is not the same as saying speed's increasing. Okay? For speed, we got to look at velocity and acceleration in combination. All right, so that was the other thing I wanted to mention. Okay, we need to move on. So get your notes out and now, I don't know that you need to write this down because this is stuff we wrote down back in chapter 2. But maybe you want to rewrite it because to keep your notes organized. I don't know, and I don't care. It's totally up to you. But if you are writing that down, just so you think about it here, let me just talk about chapter 4 here, and I've said it already, but chapter 4 is kind of a bunch of fairly unrelated sections. You know, a lot of times a chapter will have one section and the next section will build on that, and the next section will build on that, and the next section will build on that. This chapter is more like, you know, just one kind of unrelated section after another, except for one important factor, one important connection. Each section has something to do with derivatives. That's the key. If you look at the title of chapter 4, it's applications of derivatives, or using the derivative, or something to that effect. Let me see. It says using the derivative. That's the title of the chapter. Using the derivative. So we've now learned how to do the derivative of all these functions. So we're going to now cover a bunch of important applications, important ways the derivative can be used to help us do some things. Okay? All right. Well, one is differential equations. So the first thing we're going to do is section 4.1, and it's some more about differential equations. So we did a little bit of them in chapter 2. We had a little bit of one, you know, remember the T-chart, verify solutions, that kind of thing. We're going to add a little bit to it today. Okay, so first of all, review this. Differential equation is equation with derivatives. The solution to a differential equation is the original function, f, y, you know, p, whatever. Okay, we had 3 types of differential equations, right? We have the type we can just solve by doing an antiderivative. So if you have y prime equals 3x plus 2, we can just do the antiderivative straight away. Okay, that was called, sometimes we threw an initial condition in there, so it was called an initial value problem, IVP sometimes, right? This was called the general solution, had a plus C on it, but if I give you the initial condition, you can figure out what that C was. Okay, then the second type we said we were going to memorize. Now, you can notice I've added one onto there, and we actually talked about this one. So the first one was that exponential growth, y prime equals k times y, was a e to the kt. Now we're going to add this one too, and that's Newton's law of cooling, which we're going to talk more about here in a minute. We're going to do some problems. So that's another one we want to work on. But those are the 2 we're just going to, you know, use. So here in chapter 4, we're going to use. You'll probably see a problem like that on our next quiz here before Christmas. Newton's law of cooling. And if you remember what it was, this was on our last quiz where you guys had to say if K was negative, right? Or K was negative, remember? Because this was the temperature of the coffee. This was the room temperature. Coffee will be bigger than the room temperature, so this will be a positive. The bigger this is, the more it cools. Okay, that was the problem. That was the Newton's law of cooling. And it ends up being this solution right here. The room temperature plus AE to the KT. Okay? And it kind of makes sense, because here's what the graph looks like. The graph just looks like this. It's shifted up, which the big T would be like a shift up, and the coffee's just coming down, and it's cooling, and it's just leveling off right at room temperature. So it makes sense that it's cooling faster in the beginning, and then slows down, and then it just kind of levels off right at room temperature. Okay? All right, so it kind of makes sense. That's what it looks like. All right, then the third type was, hey, we don't know how to solve it, but we could verify. We could verify the solution, right, with the T-chart. We could show that something is a solution. Now, notice I also added something else over this is the other new thing we're gonna do today. We can approximate the solution by drawing what's called a slope field. Okay, and those are the two things we're gonna do today. The Newton's law of cooling, and then approximating solution. Now remember, the solution is the original function. So what we're gonna do is we're gonna, sure, sometimes we can find the original function by just doing an antiderivative. Sometimes we know the original function just because we memorized what it is. Sometimes they tell us the original function and we just verify that it is. What we're gonna do here is we're gonna graphically graph. We're gonna graph the original function. Kind of a sketch of the original function. Okay, which you'll see here in a little bit. Okay, so let's first do a Newton's law of cooling problem. Okay, so Newton's law of cooling, right, which you already kind of wrote down there. You already kind of wrote this down, and I kind of drew that picture, so maybe you don't need to rewrite it. But so Y is the temperature of whatever the object that's cooling, and T is the room temperature. Okay. All right. So here's our solution right here. So the A is some unknown constant. The K would be given to you in the problem probably, but you can find it. Or maybe the K isn't given to you, or the A is not given to you, but you're given maybe two initial conditions, and we could find the A and the K, and that's what we want to work through right now. Okay, so here's the problem we're going to do. Okay, we got some coffee, 190 degrees to start. The room is 70 degrees. After 4 minutes, the coffee has went down to 170 degrees. So what we want to know is how hot will that coffee be after 9 minutes? And we want to know how long is it going to take until it gets down to 100 degrees. Okay. So the reason we want to solve differential equations is we want to be able to use that equation to answer these questions, right? We want to be able to plug into that equation. So what information does this tell me right here? That it started out at 190. That's, put it into math notation form. Would be Y prime. Y, how about I do Y, let's treat it as a function. Y is the temperature, you're right. Y of 0. This is capital T, right, yeah. The 70 there is big T. But I'm just talking about this information right here. Y of 0 equals, Emily, 190, right? That's an initial condition that they just gave. This is an initial value problem, right? I got a differential equation because it's Newton's law of cooling. And I've got an initial condition. I actually have two initial conditions. What's the other one I have? Y of 4 equals 170. So they have given me these two pieces of information right here. They didn't write it in math lingo, but if I write it in math lingo, it's going to be better for me because it's going to help me know what to do. Okay, thank you, all right. So, what are we going to do with that information? Well, we're going to take our Newton's law of cooling problem, and like Max said, or somebody said, the T, big T, is going to be 70. The room temperature is 70. So you just got to know, if it's a cooling situation, you just have to know this equation. AE, big T plus AE to the KT. Just got to know that. That's what Newton's law of cooling is. That's the equation. So if we're doing a cooling kind of a problem, boom, you start with this right here. So we know 70, so we're going to put a 70 right there. Okay, now, what are we going to do next? Plug in, I would always plug in 0 first, something good is probably gonna happen, okay? Ignore this over here for right now. So now, here's where people a lot of times say, oh, won't that be the A? Won't A be 190, right? We always talk about A being the initial condition. No, not in this one. Not in this one. Where do we put the 0 here? Little t, right? We put the 0 in for little t. Now that's going to give you e to the 0, which is 1. And then so you're going to have A plus 70 equals 190. So what's A? A ends up being 120. Right? A ends up being 120. Now it's just 70 plus, 120 makes the 190. So there is a connection to the 190. Okay? So A is 120. So now we just take that and we stick it right back in there. Right? So now, over here to the right, we've now got it reduced down to this. So one of our initial conditions helps us find one of our unknown variables. Okay, so that we found the A. Now we can find the K by doing what? Putting that one in. Alright, so sometimes they just tell you the K in the problem, and that's nice. Saves you a step. But here we got to find it. So we put our 4 in for T, and so that's why I wrote Y of 4. I wouldn't have had to, but Y of 4 just reminds me, oh, I'm plugging in a 4. And I have to get out a 170. So my equation is 170 equals 70 plus 120 e to the 4k. Now I got to solve that. Now, let's assume this is a calculator problem at this point. Okay? So go ahead and get your calculators out. It'd be a good thing. Probably should have had the hats on today, but we don't have to do a whole lot of. Nah, we should. Let's do that. Let's get the hats. Then I don't have to do much. All right, pass them around. Hats are coming around here. Gotta have the hat on for the more here. Then Max, you're gonna be the presenter. That's what you get for setting over there. I think that was your choice. All right. So we'll get to the calculator set, but so now we're just gotta solve. We just want to solve that right there. Now we could go through and we could subtract 70 and divide by 120 and do the ln on both sides, right? And you might have to on a no calculator thing. I'm probably on this next quiz. This is probably going to be a calculator. Now you still have to write this down. You still need to show me you're finding this stuff, But now we just do a solve on that, right? So let's just go in here and do a solve. He used X, which is fine. I don't know why he solved for W. Oh, okay, solve for X. You can use T, whatever. Now, it gives you that. A lot of times I'm going to say, I don't want that. I want a decimal. You could write that. That'd be fine. But there it is. There's your K value, right? We expect it to be negative. We already talked about why it's negative, right? I would keep a bunch of those decimals probably, but we can copy and paste or, type them in again, that stuff, whatever. So, I found my K, right? So now I've got my actual equation. Right? So now I've got my actual equation. Okay, so I found big T was the room temperature. I used my initial conditions to find A and find K. And now I can answer the questions. What was one of the questions? Yeah, and how hot was it after 9 minutes? So how would we do that? How hot after 9 minutes? So the 9 in for T, right? So you can do that in your calculator. So I like to write it out. You wouldn't have to. It would be good to maybe write Y at 9 or whatever, so hey, that's the one I'm solving here. But we just want to take and put a 9 in there. So yeah, since you're just gonna do that this one time, I think it's probably, don't forget the 4, or no, not the 4, the negative, yeah, you gotta type in that. And I would type in 45803 now whatever, yeah, type them all in. Okay, 104, we wanted 3 decimal places, so 149, point 620, 149.620. Okay, and then of course I already showed you this one, and then this one, when will it be 100 degrees? Well, that's your output, your Y. So now it's a solve. So now on your calculator, this time it's a solve. So you make sure you can do that on your calculator, right? Okay, so when we're just plugging in a 9, we don't do a solve, right? We're not solving an equation, we're evaluating an expression, right? We're just plugging a 9 in and getting that value. But here we're actually solving this for x. And I like the fact he put all those decimals in there. Probably don't need them all, but 5 or 6 would be good because we want this answer to be accurate. You know what? Just grab your solve again. I'm just curious. Grab your solve and go in here and delete these, except just put 046. Yeah, delete those and put 046. Let's say we would have rounded to just 3 decimal places. Okay? Was it that far off? Oh, man. Yeah. See what I mean? So you use a rounded value in your calculation, you are not going to get your answer here. Now, is that what I have? Oh, that'll be embarrassing. 414. Okay, good. Whew. But now, well, let's say you'd only done about, you go up and grab that one again. Like I said, 6 is what I typically do. So let's go 045580. There, go with that. Okay. Now that got it, but look at it there, I had 415 where it's 4142, right? And so 414 is okay. Here you go 415, that'd be okay. Now, although that value, if you had 415, I don't know if that would, you know what I mean? And that's why a lot of times I'll truncate this. Even if I see 4 and 5, I won't round it. I'll just truncate. So good lesson there. Even if we went out 6 decimal places with that one, it starts to vary a little bit. So you want your final answer to be accurate in the 3rd decimal place. And so using rounded values along the way is not great. And that's also why it's not a horrible idea. I can't do this as Max. So scroll back up, Max. It's not a horrible idea. Keep going. It's not a horrible idea to use this as your K. You know what I mean? Because that's exact. And then on your final answer, do the decimal. So it's not awful to do that either. Okay? So, all right, that's good. All right, moving on. So that's Newton's Law of Cooling. I mean, there's not much else to tell about that. We've done some problems like that already. It's a quick review of differential equations. So if you have some homework problems where you have to do that, you know, that's about all you can do with Newton's Law of Cooling, right? You either plug in the time, or you plug in the temperature, you find the time, you plug in your initial conditions to find the A and the K, and that's pretty much it. There's not a whole lot else that goes on with the Newton's Law of Cooling. Now, they might give you a verify kind of situation or something to review that. Okay, let's go on to the second part of this today, the slope field. This is the new part. The slope field is a graphical approximation to the solution of a differential equation. And remember, what's the solution to a differential equation? The original function y. So what this is like the graph of f. So it would be like, well, I'll tell you exactly what it would be like. Let me see what else I have there. I don't think I have anything else on this page. It would be exactly like doing this right here. Did we do this in chapter 1? I gave you an f prime graph and you had to draw the f graph. Weren't we solving a differential equation? Weren't we finding the original function? Absolutely. And that's what solving a differential equation is you got something with the derivative in it, which is this, and so a slope field is the graphical picture of the solution of the original function. So let's just do this one together real quick right here. Now, this isn't a slope field, but I'm going to show you the connection here and then what a slope field actually is. Okay, so let's say I gave you this f prime graph. Okay, so you tell me where to start my f graph. We don't know. Remember that plus c, that vertical shift? So let's just say I start it down here. And why did I start it down here? Because I could see f prime is positive a whole bunch of the time. So what's that mean f's going to do? F's going to be increasing this whole time till here, right? What do you got right here? Remember this stuff? Feels like a long time ago, right? Local max, right? F prime goes from positive to negative, so F goes from increasing to decreasing. So we got a local max right there. Okay, what do you got at these points? No. No. Those are inflection points. No. It's not. It's only, no. This doesn't say anything about when F is going to touch the x-axis, because remember, F can be shifted up and down. We don't know when it will touch the x-axis. These are inflection points, right? Because F prime increasing means F is concave up, and F prime decreasing means F is concave down, right? Those are max and mins on F prime are inflection points on F. Those are the inflection points. Okay, so that means this graph is going to be going up, but it's also going to be concave up, right? Now I'm going to have to get this straight up. Any chance to do this right. Okay, so this is going to be increasing and concave up till there. Then it's going to be increasing and concave down till there. Then it's going to be, oh, now, should I have made this flat right here? Is this a flat spot? No, because if it's a flat spot, this would have been down here. See, so that's bad. I should not have done that. Okay, I should not have flattened that. So it's increasing and concave down until there, and then it's increasing and concave up till there, and then it's increasing and concave down, and a local max, right? Right there. And then it's going to go to decreasing, and then I got another inflection point there, decreasing and concave down, and then decreasing but concave up, and then it flattens right there, right? Because now I'm back to 0. So the slope here has to be 0, right? So wouldn't that be kind of a picture of F? Now, here's what's wrong with that, is I have no idea how steep, I did not take into account how steeply it goes, right? I really don't know. I mean, this is the general shape, but without knowing what these actual Y values are, right? I don't know the actual steepness. I didn't calculate any slopes and actually figure out how fast for it to go up, right? I just said it's going up. So this is a rough approximation of what F would look like. But what if I wanted to know, what if this was, say, 6 right here, and I wanted to know, and all I was given was F prime, and I wanted to know F of 6, roughly. Would you have any confidence in that Y value right there? You shouldn't, right? Plus, now I would have needed to have some initial condition here to start it, right? Because who knows where I was supposed to start this. But let's say I would have been given, that, right? So right down here is -5. So I started this thing at -5, right? So I was given, let's say I was given an initial condition of where to start it. Again, would you have any confidence in that Y value? Not a lot, right? Not very exact, for sure. Well, that's what we want to do. We want to be given an F prime and an initial condition and be able to find some F value with a little bit of confidence, okay? Now, obviously, if we can do an antiderivative, that'd be great, right? But there are a lot of them we don't know how to solve, so how can we do it? So that's where a slope field comes into play. All right, so if you wouldn't mind drawing yourself a quick little sketch of this picture right here, and even if you do mind, All I've done is put dots. I mean, I could make a grid here. I don't think my grid, let me turn on the grid. I don't think my grid fits this here. No. And that's okay. I knew you wouldn't have a grid either. Unless you got a composition. Now we'll do a little bit of this on the AP test. You typically have to sketch a slope field. Not always. And the other thing you have to do is match a differential equation with its slope field. The calculators will draw slope fields. I'm going to show you that, but it's not something we ever really use. It's almost always asked in a no calculator kind of situation. But I'll show you how it does it. You are going to need to be able to go onto your calculator and put in a differential equation for something we do later. But for this quiz coming up here, you won't have to. You won't have to do this on your calculator. Okay. All right. So what we do, if you got that made, is so basically now. Let me label this grid. It's important. I label this. This is my Y, right? This is my T axis over here, and this is my Y. What I'm about to draw, what I'm wanting to draw here is the original function. I want the solution to the difference equation. So I want the original function Y. Well, what I have is Y prime, right? So it's a lot like this. I had F prime. I was trying to draw F. But I want to be more exact. I want to actually calculate some of my slopes. So this is what I'm going to do. And I can because I have an actual equation for Y prime. So if I put a 1 in for T, if I put a 1 right there for T, what do you get? What do you get? 1. You get Y prime equals 1. Well, what's Y prime mean? The slope of Y. So on this graph, when T is 1, which means all up and down this line right here, right? When T is 1, my graph's going to have a slope of 1. So what I'm going to do is I'm going to put what I call slope segments. I'm just going to draw little slope segments that look like they have a slope of 1. Slope of 1 is like 45 degrees. See what I mean? My graph, the Y graph, the graph I'm trying to draw, when it goes through that vertical line right there, when it goes through there, it's going to be going through with a slope of 1. And then you just keep going. Now let's plug a 0 in for T. What do you get? -1. So that's on the Y-axis, right? So that, when it goes through there, it's going to have a slope of -1. Right? And now we got to do all the dots, so let's put a 2 in. What do you get when you put a 2 in for T? You get 3. So that's just steeper, right? So going through there, we're going to have, so I just going to have a slope of 3. And then put a 3 in for t. 5, steeper yet. And then -1. So it's nice. I didn't have to plot all 30 of those points. Now, why is that? Because all I had in here was t, right? If this differential equation would have had t's and y's in it, then at every one of these points I'd have gotten a different slope, right? So like at 1, 1, I'd have to put a 1 in for t and a 1 in for y and get the slope. And then at 2, 1, I'd have put a 2 in for t and a 1 in for y, you know what I mean? And that would have taken a lot longer to draw. So it's a lot nicer. But you get a picture of the slope field. So what you're going to notice, and this is one of the things you're going to do is a matching exercise today, and I'm not going to tell you a whole lot of hints, but this is one of my big hints right here, is when you've got just vertical columns where the slopes are the same the whole time, that means you only had t in the differential equation, or x. Because whenever you move to a new x, you get a new slope. But when you go to a new y, when you change your y's, right, the slope doesn't change. So y is not involved in the differential equation. So vice versa, you might get, like if we had the Newton's law of cooling one, right? The Newton's law of cooling, which is y prime equals something times y, then every time you go to a new y, you would have a new slope. But when you went this way, right, you wouldn't get new slopes. So you'd have horizontal rows where they'd all be the same slope. Does that make sense? So you're either going to have a differential equation that just has x's in it, just has y's in it, or has both. If it has both, then you're going to have a whole mess of slopes, right? You're going to have stuff, just those little slope segments where you're changing all the time. Okay, that's a way you can do a matching exercise, matching a certain slope field. Now you can also plot some points. You plot a few points, and you put them in, and you see what the slopes are, and you process of elimination, you can figure out which one is which. Okay, so a little bit of a hint there. Anyway, you put in -1, what do you get? -3. So you have a -3 slope here. Now I should mention, so now let's imagine, now I've changed to blue here. Well, I'll keep it red. Now let's imagine I've given you this initial condition. Right? So what's that mean? On this graph, it starts right here. Now, let's go to the right. Now, where should this graph go? Down, then what? Is it going to be like a parabola? Or is it going to be a parabola? Look at this equation. What's the y equation? This is actually one we could have solved. It's y equals t squared minus x, t plus some constant. And then if I know the initial condition, y of 0 is -1, I put a 0 in there, the c is actually -1. So this actually is going to be that parabola right there, isn't it? Right? It's going to be a parabola. And do you see, I mean, if you kind of squint a little bit, you look at the red slope segments, do you see a parabola there? Sure. Right? It's coming down, shoot, and it's going up. Right? You can see a parabola there. But shifted, we don't know where it is. But if you've got this initial condition, now I can come down, and I actually know it'll come back through this point, actually, because I know it's going to have, I think it's going to have the vertex is right going to be there at a half. But that's fine, doesn't matter. And we're just going to, and what I call go with the flow, right? When we sketch a slope field, we're just going to kind of go with the flow of the little segments. It doesn't have to go through them. It doesn't have to go through the different segments. It's just going to go up and up and up like so. And on this side, it's going up and up like so. And it's just kind of going with the flow of the segments. It doesn't have to go through certain segments. It just has to kind of go with the flow of them. But if you drew one here that kind of went down and went this way, when the slope segment was saying it's going up like that, it better, your graph better match as you draw it, it better be matching. This probably should have went a little steeper right through here. It better be matching kind of what your slope segments are. Now, is that a better, would you have some confidence in, if I said, what's y of 2? You know, maybe not a great deal of confidence, but maybe a little more confidence than the other one we did, right? Than this one, because we actually calculated some slope. So it's still just an approximation. It's still just kind of a guess at what the original function is. And of course, we know what this one is because it's one we can solve anyway. That's a slope field. That's a slope field. Okay, get your calculators out, and let me just show you one last thing, and we'll talk about another problem. But okay, so on your calculator, let's go into the graph in the menu, and let's go into graph entry. I don't think you're going to have to do this for any of them in your homework, and you're not going to have to type these in for our next quiz either. But go down to differential equation. Okay. And notice it says y1 prime. Now notice it says x. So it's not t. T is not the input like it was with parametrics. X is the input. Y1 is the output. So we got to make sure we understand it's y1, not just y. So this says y1 prime. So what do we want to put in here for our equation? But we can't put 2t minus 1. We got to put 2x minus 1. We got to put 2x minus 1. So differential equation, we got to use x again. Okay, now, we also had, well, let's just leave it at that. And this is for the initial condition right here. Okay, but let's don't put that initial condition in yet. So just put 2x minus 1 and hit enter. Oh, that other graph stays there? Dang it. Okay, go back to your menu. Go back to your menu. Go back to menu. Go to graph entry edit. Go to function. Go up to F1. Delete that. Hit enter. Okay, now go back to, there you go. Okay, so you're fine. There's your slope. Does everybody's look like that? Let's change the window. Go to menu, window, standard, 5, just menu. Maybe that is standard. That is standard. That's not very good. I don't like that very good. It doesn't, I don't see a parabola there quite as much, right? Okay, let's do this. Go to menu, window, menu, window settings, number 1. Okay, let's go negative 3 to 3. Let's do that and then hit enter. Leave the y's the same, it's fine. That's okay, it's coming. Isn't that better? See, can't you really see a parabola in there now? Right? And that's just showing you those slope segments now. Okay? Now let's go into the settings on this thing. Go to menu, go down to settings, 8, number 8 there. And, no, I don't want that, I'm sorry. Escape out of that menu. Let's go to, window, that's where we're. Window, let's go back to window. And let's go to window settings. Okay, and it's arrow down. See, this shows you how much we use this. Okay, here, I guess I don't care about that. I know the shortcut, but I want to, okay, go back to menu. Go back to settings. Arrow down. Can't seem to escape. Oh, I know the problem. Go back to menu. Graph entry edit. That's where we're at. Differential equation. There you go. Arrow up. I remember where it is. We got to click on this little thing with the 3 dots. Now you can tab over to it, I think, and hit enter when it's highlighted. Right there where it says edit parameters. Now, we're not going to have to do this. Okay, does everybody say Euler? That's how you pronounce that, right? It's Euler. It looks like Euler, but it's Euler. Euler,
Let's go to row.
and then a 1, and then a slope. Yeah, there's another one under there, Runge-Kutta, but it won't look much any different, really. Slope, and this we usually just all leave. Keep going down, -10, plot start, -10, plot in 10, points, plot step point 1, field resolution 14. Does everybody have those numbers? Okay. Those are good. Those are good numbers. I didn't know. Again, not going to be a big deal because for our quiz, we're not going to have to go into this. But later in the year, we're going to have to be able to draw and trace on these. Okay, hit OK or cancel, whatever. Okay, so anyway, now let's put in our initial conditions. So now let's go, so hit your tab or go back into your menu entry if you just tab. Let's put in 0 and -1 was our initial condition. And then it'll actually draw in our solution for us. And notice it doesn't actually do a solid graph, but it does dots. Well, it's actually calculating a bunch of different y values, okay, for us. And we're going to learn later on how we'll calculate those different values there when we talk about Euler's method later in the year. But that's our, there's a slope field, okay? All right, so lastly, excuse me, I want to show you this is the AP test from 2015. This is the actual AP test. Now, this is the international version, actually. The international version, and I think I told you this, they do one here in the States, I think overseas, because of the time zone differences, just for test security, whatever, they have a separate version. But they're very, very similar. And so this was an actual test. This was on the free response section. This was problem number 4. There's only 6 free response questions. It's half your grade, right? So you can tell differential equations is one of the kind of big topics that's going to be on there. And here they give you this differential equation right here. And they say on the axis, sketch a slope field at the 12 points indicated. Well, you notice this has both an x and a y, right? So that means you're going to come down here, and here's a point, -1, 0. So you're going to put a -1 there, you're going to put a 0 there. 0 minus 1 is -1, times -1 is 1. That's 1/4. So that's going to be a slope of 1/4. That's going to be pretty shallow. Help me out if I do something stupid here. Put a 0, 0 in, this will be 0. So that's going to be flat. Okay, 1, 0, that'd be a 1 times -1, that's -1/4. So pretty flat like that. Okay, -1, 1. So -1, 1. 1 minus 1 is 0. So anytime the y is 1, so then to speed this up a little bit, right? Anytime the y is 1, aren't you going to get flat? You're going to get 0 slope. So anytime the y is 1, so that was what I was talking about. If you get a differential equation that just has y's in it, you'll have the same slopes. They won't all be flat, but they'll be the same when you go across horizontal. Okay? And anytime x is 0, so anytime up here, you're going to have flat, right? So now 1, 2, so if x is 1 and this is 2, 2 minus 1 is 1, 1 times 1 is 1/4. So again, pretty flat. -1, 2. So you put a 2 in here, that's 1, times -1, that's -1/4. So again, pretty flat.
Backwards.
I did.
Isn't the 1, 2 supposed to be positive? Oh, it is.
Okay, 1, 3. So if I go 3 minus 1, that's 2 times 1 over 4. That's 1/2. So a little bit steeper. And then I'm guessing this one's going to be -1/2. So a little bit steeper than that one. Now that's kind of an interesting one. There are a lot of flat ones and a lot of slopes that aren't, but they're gonna grade it basically and see that your directions are kind of going the same way and your steepness is in the ballpark, I think. But there's your slope field. So it looks like, now depending where your initial condition is, if it's down here, it looks like maybe it's going to do something like this. If it's up here, it's doing this. When you get a whole row that's 0 like that, what do you think's going on there? And like a horizontal asymptote usually. But a lot of times when this is flat, that's like a local min or a local max maybe. But you get a whole row across here that's flat, you probably have an asymptote situation. Or you have, what's happening here is you have different branches. So kind of like a hyperbola kind of a thing, right? In other words, if you get an initial condition down here, it's going to do this. If you get an initial condition above this, it's going to do this, right? And so depending where your initial condition is, you might have a different branch. Okay, so that's just it. I mean, so that was an actual one part of an AP test question, and most years it's on there. Not every year, but most years it's on there. And then they do this, and this is actually a problem we can do. Okay, this doesn't have anything to do with slope fields, but it does. We've talked a lot about equations of a tangent line. Okay, so this would be worth reviewing here real quick, and then this will be our last problem. Let y equals f of x be the particular solution to the differential equation with this initial condition. Okay, so the differential equation was y prime equals x times y minus 1 over 4, right? That was the differential equation. And they've given us this initial condition. And notice they've said y equals f of x. That's why they call it f here and y up here, right? Y and f are interchangeable because they wrote that right there. Okay? Write the equation of the tangent line at the point 1, 3 and use it. Well, let's forget that part for right now. We'll get to that in a minute. But we should be able to do that. Write an equation of a tangent line. What do you need for equation of a tangent line? Slope and a point. And then we're just going to go y equals slope x minus point plus point, right? What do I put in for the point? 1, 3. How do I get the slope? Right? They gave it to me. This part of this should be so easy. It's almost embarrassing to be on the AP test how easy it is, right? It should be easy. Equation of tangent line. We need a point and a slope. They gave us a point, and now all we got to do is put a 1 in. I think we already did this. And a 3. This was 2. 2 times 1, 2 fourths. That's 1 half. Now, the new part, the part we haven't really done as a problem, but we've sure talked about that idea, use it to approximate f of 1.4, because we don't know the original function f, do we? Right? We haven't solved this differential equation. We want to know f of 1.4, but we do know f of 1. We know f of 1 is 3. So just think about the f graph. If at the point 1, 3, let's pretend, I don't know what this curve does, but let's just pretend. I didn't want to do that.
Even exists.
Huh?
It says it's a function if it has an x value of 2 different values.
What do you mean an x value of 2 different y? Of what?
Because it says evaluated at 1, 3 and 1, 4. It's just at 2.
What? No, 1.4.
Oh, okay.
That means plug in a 1.4. Okay, so what I'm saying to you is, and I'm sorry, this is the f graph. So if the f graph, so let's just say at this point, let's say the f graph came through, I don't know, whatever. Let's say the f graph went through this point right here. And here, what we just found is our tangent line. Are you with me? We just found the tangent line right here. Right here would be 1.4. Right? A little bit past 1 would be 1.4. Do we have an F equation that we can plug that 1.4 into? No. But couldn't we plug a 1.4 into the line equation? Wouldn't that y value on the line be pretty close to the one on the curve? Do you see what we're getting at? When we first talked about, we talked about locally linear. When we talked about tangent lines, we said that the tangent line touches a curve at one point. But if you just look at a really close area around that point, the line and the curve are pretty much the same thing. That's what this is saying. Use the tangent line to approximate f of 1.4. In other words, they're saying don't plug 1.4 into the f equation because we don't have one. Plug 1.4 into the tangent line equation. Because this point on the tangent line at 1.4 is darn close to the point on the curve at 1.4 because it's near 1. It's now, if it was way out here at 7, right, now the tangent line and the curve aren't going to be very close. But right around 1, the tangent line and the curve are going to be pretty close. So we can put a 1.4, and this would be a no calculator problem, right? But it's easy. I mean, 1.4 right here. So 1.4 minus 1 is 0.4. Half times 0.4, 0.2, 3.2. That would be the answer to that problem. But you could get some partial credit, but for just finding the tangent line, right? If you didn't know what to do with the 1.4, whatever. But that's the idea. Use the tangent line approximation to a curve is basically saying, hey, when the tangent line when you draw the tangent line on the curve, it touches a curve at one point. So the line and the curve both have the point 1,3. But the points around that point, the points on the line are really close to being points on the curve. So we can plug into the line equation because it's easy to find. And then we can find a y value to be pretty close to the curve. Okay, that doesn't mean do with slope fields or anything, but it's just another kind of tangent line example, and it's working with the differential equation because the differential equation gives you y prime. It gives you the slope. That's what it is. It's an equation with a derivative. All right. So basically what you're going to be doing, and we'll go over that tomorrow, but basically that's it. So what your homework's going to be in 4.1, the 4.1 homework questions, I gave you that sheet yesterday. Okay, it's not very long, so you should finish up that on that packet. Do that number 4. Do that number 4 on page 9, that one with total distance. Do it like we did the one on the front page, number 11. Okay, do that one. And finish up any of that packet you didn't do. Okay. Up through page 16, I'm saying. Up through page 16. But on 4-point homework, you're going to be doing some matching of some slope fields. Okay, they're going to have some slope fields, and so you're going to kind of use those hints I gave you with, if the columns up and down have the same slope all the way across, right? If each column is exactly the same, that means it only has x in it. If it's going across the same slope, it's only going to have y. If it's a whole mixture of slopes just changing all over the place, it's probably got x and y. But then you're going to have to plot some points. You're going to have to plug some points into the differential equation to see exactly which ones are which, to match them. So there's going to be some of that, and then I think there's going to be a little bit of Newton's law. I don't think you have to draw any slope fields. Now tomorrow I've got a worksheet or two, and we're going to actually go into some drawing of the slope fields and so forth, and matching and doing some of that. And then we're going to get started on section 2. I don't know if we'll get started on that tomorrow. We might get started on that on Friday and Monday. And we got our quiz next Wednesday. Okay. So, all right.
We have a speaker tomorrow.
Today and tomorrow. Today and tomorrow, and I think that's it.